meeting, as I've just pressed it. Okay. All right. Thanks, Asha. Yeah, welcome to our webinar today. We're going to tell you a little bit about our Carbon Week survey. My name is Daniel Hayhow. I'm the research lead in urban biodiversity, urban wildlife at Earthwatch. And I've been at Earthwatch for 2 years and involved in the Tiny Forest programme. I'm here with Claire.
Hi, I'm a research manager at Earthwatch. I've been involved in the Tiny Forest programme for a year and at Earthwatch for 3 years.
Hello, you guys know me, so I'm Divya, the person behind the Tiny Forest inbox. So yeah, I'm the community engagement coordinator, and yeah, nice to see you all virtually, and hope you had a good day today.
So we've prepared a little bit of a presentation just to run you through some of the results of Carbon Week. So I'll just share my screen now and share that with you. And then stop us at any time if you've got any questions during it, but also lots of time for questions and chats at the end. I'll just share my screen. Start the PowerPoint. Okay, so what we're going to go through is we're going to quickly talk about why is carbon storage important, how we calculate carbon storage, the results from Carbon Week, and what's coming up next, and then any questions that you might have. So why is carbon storage important? Well, as we all know, increases in atmospheric carbon lead to increases in global average temperature, which is climate change. And climate change is causing a huge number of problems in, well, for the world. And we particularly feel them in our urban environments with the urban heat island effect and with the corresponding changes to biodiversity. It's a big driver of biodiversity decline and impacts on flooding and things like that. So it's an important, so carbon storage and getting carbon out of the atmosphere, reducing the amount of carbon in the atmosphere is incredibly important. And trees and other vegetation do this through photosynthesis, where they take in carbon dioxide from the atmosphere, they take water up from the ground through their stems, and they use the sun's energy to transform the carbon dioxide and the water into oxygen that they release, and glucose, which is where the carbon is, that is stored in leaves, roots, and trunks. And we're not trying to, tiny forests are obviously tiny. And as much as we'd love to, we're not actually trying to grow the Amazon rainforest of tiny forests, unfortunately. But what we are trying to do here is understand how we can best develop these tree planting initiatives in urban environments, and what are the success factors for that and for maximizing carbon storage in these environments. So how do we calculate carbon storage? Well, you guys have gone out there and you've measured tree height and you've measured diameter, which is fantastic because we couldn't calculate any carbon storage without you. And so we use the height and the diameter to calculate the green weight of the tree. When the green weight means that it's the weight when the tree is full of water, when it's lush and green and beautiful. And so what we do is we take a constant of green weight for trees generally. We times that by the diameter squared, and we times that by the height. And diameter squared times height is the volume of the tree. And then this constant that we use is the constant that gives us the green weight. We then need to calculate the dry weight because water isn't carbon stored. So we calculate the dry weight, and that's and dry weight is sort of if you took a plant back to a lab and you dried it out in an oven for hours, that's your dry weight when all the water is removed. And what researchers have come to understand is that dry weight is about half of green weight. So about 50% of the tree is water. So really nice and simply, we just take our green weight calculation and we times it by 0.5. And that gives us our dry weight. To calculate the carbon stored, well, not all of that dry weight is carbon. Glucose is C6H12O6. So it contains also hydrogen and oxygen molecules as well. So not all of the tree is actually carbon. So researchers have looked into the makeup trees and discovered that, that the dry weight is about 50% of the dry weight is carbon. So nice and simple, again, we just times our dry weight by 0.5, and that gives us the amount of carbon stored by a tree. But we've got 600 trees in the forest. So we have to times our average of all of the trees that you've measured, we times that by 600 to give us the carbon stored in your tiny forest. Now, what we do want to do, and what would make this more precise, is we want to look at two bits differently. We want to look at the green weight and actually calculate that for each species, rather than as a constant across all species. The other thing,
we know that trees grow differently.
They
so
do.
You'll have seen of the trees you measured, some of them were much, much taller than others. Some of them get a wider stem or multiple stems. So we're losing some information by just using one number across all of our species, and by figuring out and working with other researchers to get that number, that species specific green weight, is going to be really important to making this estimate much more accurate.
yeah. And then the next thing we want to do is we want to look at using each species individually, like how many of each species are in the forest, and using that species average to calculate the and adding those together for all of the species in the forest to calculate the carbon stored in your tiny forest. So what we're trying to do here with our next steps is to make this a much more accurate estimate of the carbon stored in the forest.
All of our forests, you'll know the one you've been involved in and visited, has a certain group of species in it. Each forest is different across the country. And that's one of the really great things about tiny forests. Each one has a different composition of species. Some might have more oak trees, some might have beech trees, some might have more hawthorn. And so if we were to just use the same numbers across all forests, we'd again be losing information. So the information you're going to give us is going to be the same. You can keep getting out there and seeing how your trees are growing, but we can keep refining these methods and getting better and better information based on your data.
So, well, I see something in the chat, so should we just see what, oh, that's Asha saying hello. Hi, Asha. So what are the results? Well, Carbon Week, and it was only 1 week, was incredibly successful. We had 772 surveys submitted across 21 different tiny forests, measuring 40 different tree species. So well done, all of you. That's an amazing, amazing effort.
And it's the first time we've tried anything like this. We've worked with different people where we've been on site, and we've worked with you, taught people how to do it, and kind of showed them. This is you going out there and doing it yourselves, and hopefully, you know, learning and getting a load of enjoyment out of the process. So just to see that on our first attempt has been like really engaged loads of people, we're really, really happy about that.
Yeah. And so here is the results. How much carbon did your forest store? So we've split these out into forests that are 1 year old, 2 year old, and 3 year olds, because not all of our forests have been planted in the same year. We've planted our first in 2020, and so we need to account for that. And what you can see is that there's a huge amount of variation in how much carbon forests are storing, but that if you look over time, it is increasing over the years. So we are seeing more carbon stored in year 2, more carbon stored in year 3, which is exactly what we would expect. You can see that Oak Street here in Wolverhampton is in its 2nd year and has stored just under, probably about 90 kilograms of carbon are currently being stored by Oak Street Forest. Yeah, I don't know where the other two of you are. Do you know, Divya? So Chippenham.
One of the lower ones. Chippenham is maybe recorded.
Yeah, probably on a different day, I guess.
Yeah, so it's the year 1 forest, Chippenham, and it looks to have recorded about 20 kilograms of carbon. And there's a huge variety of reasons. This is one of the research questions that we have about tiny forests, is what affects some of their growth rate, what affects the success factors in them. And it doesn't, just because you're having a slow growth rate in year 1 doesn't mean that you're going to see a slow growth rate in year 2 or year 3. Forests do catch up. We actually had a forest that went through a terribly sad bit of vandalism. It had a fire, and we had to do some replanting, and it is now looking absolutely amazing. It's one of, I think, our best looking forests.
And the conditions that a forest experiences in its first year have a real impact on, you know, the amount of growth. So what we're looking at here is how much carbon is in them, but it's also a reflection of how much the trees have grown. Obviously, you can imagine you're measuring the heights and diameters of them. So if for instance in Chippenham, the trees that were measured might have been particularly small from their first year for whatever reason, maybe it has been a very dry year, maybe they haven't grown that much.
They might have been planted later in the season, and measured earlier in the season. That's another possibility.
So there's no way this is a competition, and it's just going to be really interesting to see over time. And this is a long-term, you know, project. And what you've got here, what you've helped record here, is that baseline, which allows us to see, right, what happens in that first year. Not many people record these data. People calculate carbon on big forests or estimate it based on, you know, big algorithms and surveys of huge trees. So to understand this at this scale with small young trees is really fascinating. So you're part of a really, really exciting research project.
Yeah, Jude is from Muttonbrook, Barnet. So yeah, I think they're probably in line with Chippenham.
Oh yeah, about the same. Are they similar? Are they both London?
Yeah, Barnet is London, yes.
Where's Chippenham? What's south? That's fair. That was an unfair question to ask Divya about UK geography.
I can't answer it anymore. So I think it's...
But you can imagine that the effects of the drought were probably particularly bad in the south of England this year, which will have impacted on the trees.
Yeah.
Does the number of trees measured have an impact on the results that you put out? Like if, for example, if I measured all 100 trees and then a different forest measured like 40 trees, would that change?
So, I mean, it would depend. Some tree species are much slower growing than other tree species. So if you happen to measure
a lot of fast growing trees,
if you measure all 100, you're getting the full variety of species in your forest. If people just happen to be like, I love oaks and I'm going to go and measure like oak trees, then what they'll see that the estimate will be low because oaks are quite a slow growing species.
Okay.
So yeah, if you've only measured a few, it's more likely to be either high or low, because we're using an average to calculate this. It's not a total of the amount that you measured. Yeah.
And so in total, across all of these 21 forests, they have stored 836.67 kilograms of carbon since they were planted. And that is, I should mention, our estimate of carbon store, the amount of carbon stored in the forest, is a massive underestimate of the carbon stored by these forests, because it only accounts for above ground biomass. It doesn't take into account, which is the shoot, the leaves and the trunk. It doesn't take into account at all the roots, and it doesn't take into account either the transfer of that carbon into the soil. So it's a real underestimate of the amount of carbon stored. But that is an amazing figure for 21 forests in such a short period of time.
It's definitely the minimum, and it would be, you know, fascinating to see if ever through other research projects we could look at soil carbon as well, and share that
over time. So how much carbon has been stored per species? So we've got when we plant species in the canopy level, the sub-canopy, the understory, and the shrub layer. And this is actually what makes tiny forest kind of one of a unique planting method, is that it has all 4 of these forest layers together. And what you can see is a difference. I've broken this down into the trees that were planted into an average for year 1, an average for year 2, and an average for year 3, and those are just stacked on top. So it doesn't, so you'd calculate year 2 minusing where year 1 is, and up to where it comes on that bar. So it's not, yeah, does that make sense? And so what we can see, and we've done that because otherwise you'd all think that eared willow was growing exceptionally well. It was the best growing in the entire forest, but this is just a measure from year 3 forest, and we don't know what species like elder that are doing exceptionally well in year 1 and 2, and the same with elmwich, how high they will be in year 3 by year 3. So that's why we split it out into the years. And what you can see is, you can see that some species are much faster growing than other species. And the species that we're seeing that are much faster growing aren't actually that surprising to us. Silver birch, elder, alder, these are all what we call pioneer species. And pioneer species, they disperse into an area and they grow super fast, and they're tall, they're fast growing and quite short-lived species generally. So we're expecting that some of these species will shoot up and take over the forest for a while, whilst our slower growing species like our oaks and our large-leaved limes and things like that will take longer to get started, but will eventually be the climax species of the forest and what should make up the forest, the majority of the forest at the end, is what we predict.
Yeah.
And also that even the pioneer species, once they die off, doesn't mean that they're gone, because their seeds would kind of get in the next batch into the forest.
Absolutely. So this is an ecosystem that's self-generating and self-perpetuating. So yes, we expect trees to die, but we also expect trees to produce some seeds that fall into the ground and create that seed bank in the soil that when a patch of light comes around will spring up, and then you'll see all of these new little treelets growing in the ground, and a few of them will come up and be that next tree. So we're not actually worried if trees die in the forest, because we expect it to be a self-perpetuating ecosystem, which is what we need the natural environment to be. It is a system that self-perpetuates and regenerates and renews itself.
And I think what's important that you said about trees dying, especially once the older trees do start dying in 100 years time, and your children's children are out there playing there, but those trees, as they fall, they take all that carbon with them, and that carbon is absorbed back into the soil as that wood rots. So again, a part of the system is that we're storing carbon now that will continue to remain in the system and into the soil in generations to come. So it's all part of that cycle.
And that builds in as well the ground biodiversity, which breaks down which breaks down the dead wood, putting the carbon back into the soil, storing it in the soil. Whereas if you take that dead wood away, not only are you removing it so it's not going to be stored in the soil anymore, you're also removing the opportunity for biodiversity, for having a really healthy soil biodiversity, which is so important for soil health.
Like fungi and beetles that actually, it's a habitat in itself.
Yeah.
Absolutely.
Oh, we've got someone joining.
Hello, Karen.
Thanks for joining, Karen.
Thanks for joining, Karen. So we're just wrapping up, but you can ask us questions and we can go back through it. But what's next? Well, soon we've got our 2022 monitoring report coming out. We're just finishing our last lead monitoring day. That will be tomorrow. So we will be prepping the science report in earnest. The monitoring